Hello and welcome to Lecture 3 of Electric Fields in Phys 1204. In this lecture we're going to talk more about the forces that are exerted by electric fields on charges that are in them. I'm going to start out by talking a little bit more about how we use electric fields to think about things. And I'm going to start by asking this question: what charges produce this field? Well, there are several possibilities. There could be a positive charge over here. However, it's also possible that a field like this could be produced by a group of negative charges over on this side. The point is that just from the field, you don't actually know what the source charges are. There are many possibilities. However, in many cases, we actually don't care about the source charges. In many cases, we have a region of space, and we are interested in the motions of charged particles moving through that space. If we know about the electric field in the region, that's all we need to know. And so we can use the electric field to replace any knowledge about the source charges, as long as particles moving through the region have no measurable effect on the source particles of the electric field. Then we can ignore those source charges and just focus on the motion of objects that move through this region. Those objects will be affected by the electric field, but the electric field is all we have to know about. And the point now is that the electric field can be thought of as the agent of electrical forces on charged particles that move through the region. It'll often be useful to talk about a uniform electric field. So this would be a field that has the same magnitude everywhere and points in the same direction everywhere. Here's a vector field diagram of a uniform field, and remember that this is not implying that there are places where the field is pointing to the right and other places where there's no field. It's just that you can't draw a field vector at every point on the diagram, or the diagram would be unreadable. So this is a subset of the field vectors. The E-fields that we've seen, which are caused by isolated charges, are not uniform. For example, the field due to a positive charge, which is certainly varying in magnitude and direction from place to place. And similarly, this field due to a positive charge here and a negative charge here is most certainly not uniform. But we will see how in practice we produce approximately uniform fields. We often talk about the force exerted by an electric field, and this is sort of a shorthand. Here's the definition of the electric field, but as I've written it, there are some things missing. Notice that there's no source subscript on the E field, and that there's no agent subscript on the force. What's going on here, as I talked about before, is that we're thinking of the field as being the thing that exerts a force on this charged particle. This field, of course, must have some source. There are source charges somewhere else, and those are actually the agents of the electric force on this charge. However, we're ignoring them, and we're just thinking of the field itself as the agent of that force. You may be a little confused because surely this charge must produce an E field of its own, and so the E field around it must be modified. However, remember that if we're interested in the motion of this particle, then just as I cannot pick myself up by my own shoelaces, this charge can't exert an electric force on itself. And so we're not concerned with the field that it produces. The only field it feels is fields produced by other charges elsewhere. And so we talk about this charge being in this field and feeling a force exerted by the field. To find that force, we just rearrange the definition of the E field. And so we can find the acceleration of the particle if this electrical force is the only force acting on it, just like this, where we now see that the acceleration is going to be parallel to the field and related to it by the magnitude of the field times what is called the charge to inertia ratio, or more commonly called the charge to mass ratio. So charged particles in uniform fields will experience a uniform acceleration, since the acceleration is just the charge to mass ratio times the E field. And so we'll have all the UAM, uniformly accelerated motion, methods that we're familiar with from Phys 1104 to use in situations like this. The acceleration is going to be parallel to the field. In the case of a positive charge, it'll point in the same direction as the field, and in the case of a negative charge, the acceleration will be in the opposite direction to the field. And the magnitude of the acceleration will be determined both by the E-field strength and by the charge-to-mass ratio. If a particle is released from rest, or if it starts off moving parallel to the field, then we'll have nice one-dimensional uniformly accelerated motion. But if it starts off moving at any angle to the field, then the motion is going to be parabolic. That's exactly like what we saw for a projectile in Phys 1104, and the physics is fundamentally the same. So if we had a particle that enters a region of uniform E field with some velocity v, its path would curve. If it's a positively charged particle, then its path will curve in the direction of the E field. If we have another particle carrying the same charge, but with 2 times the inertia, its path is also going to curve in the direction of the field. However, because of that larger inertia, it's going to have a smaller acceleration, and so its path will be less curved. And finally, a negatively charged particle is going to have a path that curves in the opposite direction. Motion in non-uniform fields is much more complicated. Here's a simple example. Let's say we have a charged particle moving towards some larger charge, such as a charged sphere. And perhaps this is a negative particle and it's moving towards a positive sphere. Note that the electrical force on this particle will be attractive. In this case, that means it'll be to the left, which is in the direction of motion. And so this charge is going to speed up as it moves at the sphere. However, we also know that the field is getting stronger as the charge moves closer to this sphere, and so the acceleration will not be uniform. That means we have various ways of handling it. You actually saw in Phys 1104 how to integrate this, or how to plug it into a spreadsheet or something like that to work out what the later speed would be. But the much easier way is to use conservation of energy. We won't see how to do that right away, but we will see how to do it later on in the course. We are very often concerned with the motion of charged particles under the influence of other charged particles. For example, at one level, that's what chemistry is all about. However, we're also often interested in the effect of charge distributions on charges. So, for example, we might think of a charged particle near a charged plate. This sort of thing comes up all the time in various types of electronics and other devices. How do we do this? Because Coulomb's law certainly doesn't apply here. We can't use Coulomb's law to calculate the force that this plate exerts on this charge, except that in a sense we sort of can. What we do is we think of breaking the plate up into little pieces, and we think of the location of the charge. Now, we can think about each little piece as if it was a point charge and calculate the field at the location due to that little piece. We do this for each little piece of the plate and sum them up to get a total field at this location. At this level, that's only approximate, because these pieces of the plate are not really point particles, and so Coulomb's law doesn't really tell us the E fields here. However, we can think of breaking the plate into smaller and smaller pieces, and in the limit, as those pieces go to 0 size, we end up getting a precise prediction for the electrical field at this location. Once we know that electrical field, we can just use our definition of the E field to get the force on our particle. I hope this is ringing bells, because this process of breaking the plate up into little bits and summing up the contributions due to those little bits and letting the size of the little bits go to 0 is exactly like what we've seen before for doing things like displacements due to changing velocities and so on, and just like in those cases, it leads us to doing integration. An idea that's important when we're calculating the fields due to charge distributions is charge density, and this is related to familiar ideas that you already know. You've certainly come across the idea of density, or more properly what we would call mass density, which is a mass per unit volume. So for example, lead has a high mass density, whereas styrofoam has a very low mass density. Or you will have come across the idea of population density, which is people per square kilometer. Well, charge density is really the same idea. We can have a volume charge density, which is a charge per unit volume of material, and so that's analogous to a mass density. We can also talk about a surface charge density, which is a density per unit surface area of some object. That's very analogous to a population density. A little less familiar would be a linear charge density, but if we're talking about a long, thin object, it makes sense to talk about the amount of charge per unit length of the object.